Hi everyone, my name is Huynh. Today I would like to present our paper, Defeating Reactive Jammers with Deep Dueling-based Deception Mechanism. My presentation today is divided into 4 parts. First, I will give some background information and motivations that led us to this research. Then I will discuss about the system model and the proposed solution. Finally, I will highlight some simulation results. First, I would like to give some background information about the jamming attack. So what is the jamming attack? As you can see in this figure, the jammer attacks the channel by sending interference to disrupt or even bring down the communication between the transmitter and the receiver. Currently, there are two main solutions to deal with jamming attacks. The first solution is frequency hopping. The key idea of this technique is that the transmitter can switch to another channel to transmit information when the current channel is under jamming attacks. And the second solution is rate adaptation. This technique allows the transmitter to reduce its transmission rate under jamming attacks. However, the two solutions are not effective in dealing with reactive jammer that we will consider in this paper. So, what is reactive jammer? Reactive jammer is the jammer that only attacks the channel after the transmitter transmits information. Conventional solutions like frequency hopping and rate adaptation cannot effectively deal with this type of jammer. The reason is that a reactive jammer with sufficient power budget can attack multiple channels at the same time with high power. Moreover, the transmitter is unable to adapt its transmission rate beyond the jamming signal because the reactive jammer attacks the channel only after the transmitter transmits data. Currently, some state-of-the-art solutions are proposed to address the limitation of conventional approach. The key idea of this solution is to leverage the jamming signal by using energy harvesting and ambient backscatter communication technologies. In particular, when the jammer attacks the channel, the transmitter can harvest energy from the jamming signal, or it can backscatter information through the jamming signals. However, the techniques are only applicable to deal with static jammers. In this paper, we introduce a novel deception framework which can effectively defeat reactive jamming attacks. In particular, at the beginning of its communication cycle, the transmitter can choose to trap the jammer by transmitting fake signal in a short period of time. When the jammer attacks the channel, the transmitter can leverage jamming signal as a communication mean to transmit information beyond the emerging ambient backscatter technology, or it can harvest energy from the jamming signal to supply for its operations through using IF's energy harvesting technique. Then, we propose a deep reinforcement learning algorithm with the deep dueling network architecture to obtain the optimal defense strategy for the transmitter. Here is the design of the ambient backscatter circuit. As you can see in this figure, to backscatter data to the receiver, the transmitter uses an IF switch to switch between two loads, Z1 and Z2, to absorb and reflect the ambient IF signals. Several prototypes of ambient backscatter have been proposed in the literature. It is reported that the data rate of ambient backscatter can be up to few megabits per second, and the communication range can be up to 100 meters. This makes ambient backscatter a very promising solution in dealing with reactive jammers. This is our system model. We consider a wireless system in which the transmitter transmits information to the receiver and the jammer aims to disrupt this communication. The transmitter is equipped with an IF energy harvesting circuit so that it can harvest energy from the jamming signal. The harvested energy will be stored in an energy storage. The transmitter is also equipped with an ambient backscatter communication circuit, and I presented in the previous slide. With this circuit, the transmitter can backscatter information through the jamming signal. The jammer have an unlimited power budget and only attack the channel when the transmitter actively transmits information. To defeat the considered reactive jammer, in this paper we propose a deception mechanism. As you can see in this figure, at the beginning of each time slot, the transmitter can choose to trap the jammer by transmitting fake signal in a short period of time. Then the transmitter listens to the activity of the jammer. If the jammer does not attack the channel, the transmitter can actively transmit data to the receiver in the rest of this time slot. If the jammer attacks the channel, the transmitter can harvest energy from the jamming signal, backscatter the jamming signal, or perform the rate adaptation technique. To capture the two decision periods of the deception mechanism, we introduce an MDP model with two decision epochs in each time slot. As you can see in this figure, different from conventional MDP, in our proposed MDP, after performing the deception mechanism in the first decision epoch, the transmitter can observe the activity of the jammer and make appropriate actions. This is our state space. Here, E and D are the amount of energy in the energy storage and the number of packets in the data queue, respectively. F denotes the deception strategy of the transmitter. F equals 1 if the transmitter performs the deception mechanism in the first decision epoch, and F equals 0 otherwise. J denotes the state of the reactive jammer. J equals 1 if the jammer attacks the channel, and J equals 0 otherwise. This figure illustrates our action space. In this paper, we have 6 actions for the transmitter. At the beginning of each time slot, the transmitter can choose to perform the deception mechanism or actively transmit data to the receiver. If the transmitter chooses to perform the deception mechanism, it will send fake signal for a short period of time and then observe the activity of the jammer. If the jammer is idle, the transmitter can actively transmit data to the receiver in the rest of this time slot. If the jammer attacks the channel, the transmitter can harvest energy, backscatter data, or perform the rate adaptation. In all cases, the transmitter can always choose to be idle. In this work, we define the immediate reward as the total number of packets that are successfully transmitted from the transmitter to the receiver in a time slot. This is our optimization problem. RT is the immediate reward when the transmitter performs an action at a given state. RV is the long-term average throughput of the system under policy fee. And in this paper, we aim to find the optimal policy fee to maximize the long-term average throughput of the system. To obtain the optimal policy of the proposed MDP, conventional Q-learning algorithm can be used. However, the Q-learning algorithm is well known for its slow convergence, especially under the dynamic and uncertainty of the reactive jammer. To deal with this problem, we propose a deep dueling algorithm that can obtain the optimal policy for the transmitter much faster than the Q-learning algorithm. The key idea of the deep dueling algorithm is to separately estimate the value and the advantage function with two streams of fully connected hidden layer. As you can see in this figure, the value function is used to estimate how good it is when the system is in a given state. The advantage function is used to estimate the importance of a certain action compared to other actions. The value function and the advantage function are then combined at the output layer by using this equation. Now I will highlight some simulation results. First, we compare the conversion rate of our proposed deep dueling algorithm with the deep Q-learning algorithm and the Q-learning algorithm. As you can see in this figure, the conversion rate of the Q-learning algorithm is very low compared to those of the deep Q-learning algorithm and the deep dueling algorithm. However, with the outstanding advance of the deep dueling architecture, our proposed deep dueling algorithm only requires approximately 40,000 chaining steps to obtain the optimal deception policy for the system. In contrast, the deep Q-learning algorithm with the conventional deep neural network architecture still cannot find the optimal defense strategy after 100,000 chaining steps. Next, we compare the average throughput and packet loss of our proposed solution with other conventional policies. The first policy is harvest and transmit. Under this policy, the transmitter can only harvest energy from the jamming signal and then use the harvested energy to actively transmit information to the receiver. The second policy is without deception. Under this policy, the transmitter does not perform our proposed deception mechanism. In this figure, we vary the attack probability of the jammer and evaluate the average throughput and packet loss of the system. Clearly, the average throughput obtained by all policies slightly decrease when the attack probability increases from 0 to 0.3. The reason is that when the jammer is not likely to attack the channel, the transmitter has less chances to exploit the jamming signals, resulting in low throughputs. With high attack probabilities, the jammer often attacks the system. In this case, the throughput obtained by the proposed solution significantly increases. The reason is that the transmitter has higher chances to exploit the jamming signal by using energy harvesting and ambient backscatter technologies. Note that the average throughput obtained by the harvest and transmit policy decreases when the attack probability is higher than 0.8. The reason is that under the harvest and transmit policy, the transmitter can only send data to the receiver through active transmissions. However, unlike the ambient backscatter communications, active transmissions are disrupted by the jamming attacks. Finally, under the without deception policy, the average throughput decreases if the jamming attack probability increases. This is because without performing the deception, there is not enough energy for the transmitter to actively transmit data. Next, we vary the successful probability of harvesting energy from the surrounding environment and observe the system performance in terms of throughput and packet loss. As you can see in this figure, when the energy arrival probability increases, the throughput of the system increases because more energy can be harvested from the environment to perform the deception mechanism and active transmissions. As a result, the packet loss is reduced in this figure. In overall, by obtaining the optimal defense policy to guide the transmitter to take optimal actions, the proposed solution always achieves the best performance in terms of throughput and packet loss. Note that in all scenarios, the conventional Q-learning algorithm cannot convert to the optimal policy, resulting in a low performance. This is the end of my presentation. Thank you for your attention.